use the kept nuts that come in the kit. We use nylocks and nylock threaded set screws. So because these robots, either when you're in the car driving to tournament or actually out on the field, they take a lot of vibration, a lot of impact. Your screws are going to loosen up over time. Nylock set screws and nylock nuts help prevent that. Also, don't transmit loads through axles. We have an example of...
Where's your example to hand around?
Don't know.
Supposed to be there on the cart?
But what we're saying with this is a picture of how we set up our drivetrain wheels. We have our sprocket. It's actually got those 4 screws. They go all the way through the 4 holes on the wheel, and we only have 1 set screw on that entire assembly that connects to the axle itself. And the axle is just for keeping everything in place and rotating around. The axle doesn't take any actual load. What we've seen happen is you'll have a hub with a set screw on your sprocket. The set screw goes to the axle, and then you have a hub with a set screw attached to your wheel on that same axle. And then all that load is going from the sprocket down to this itty-bitty set screw, transmitted along this axle through another set screw and back out to your wheel. So what we've done instead is we have these 4 screws that the standard Tetrix hole pattern comes on all of these hubs and all of these wheels. So we use that instead of putting the load through those 2 set screws.
We see a lot of people where they'll have the wheel outside, run through the channel, and the sprocket on the inside. That guarantees you have to do that. What do you guys do?
Our wheels and axles, or our wheels and sprockets are all on the same side. So, and they're actually bolted together with 4 bolts. That changes the load to a shearing force now on those 4 screws, which those Tetrix screws are pretty strong, and you've got 4 of them, and they're all at an actually larger radius than that axle. So you can see where you get a lot more strength a lot quicker. What? Yeah? Okay, the zip ties on this particular wheel, you can actually see it on our 2 robots here, but we added Lego motorcycle tire tread around our wheels, and the zip ties are just to help keep it in place. Yeah, increase your weight. All right. All right. And then understanding friction and traction. This is an important one. Surface area does not change friction. Surface area has no effect on friction. And you can see that in the formula for friction. Friction is just the coefficient of friction, which is the stickiness of the 2 surfaces, and the amount of force being applied between them. So what are the 2 factors that are going to give you, on a robot, more push, more traction, or more friction? The type of your wheels and weight. That's right. I heard someone say weight. I wasn't sure. But those are your 2 things. Having dually wheels or having more wheels, that's not going to give you more traction. We've seen teams make that mistake, and it doesn't make sense. And then the last thing to understand is the different forces on your robot as far as tension and compression. So part of this can go back to where the flat metal bends. Flat metal is fine for tension because you're pulling on it. You start getting compression, it's pushing it together, it's going to bend. So just understanding what different parts of your robot is feeling will help you design a better robot and understand where you need different shapes.
Calculating loads on lever. So this is a really important factor that a lot of teams should do to make sure that they have enough power going to a lever arm. So we use a margin of safety of 2 to 1, meaning we always have twice as much power as actually needed to move the lever arm if we shoot to.
So basically the way this works is it works the same way as the wheels we were talking about earlier. You've got your lever arm, whatever it may be, an arm on your robot, something of that nature, and you've got a DC motor and probably a few gears in between there, which you've got your gear ratio, whatever that is, that multiplies the power of your motor. Our first year, I know we had a 9-to-1 ratio off of one of the single DC motors on our arm.
I'll throw in there 9-to-1, 6-to-1, 4-to-1, 3-to-1, and 2-to-1 were Tetrix ratios we hit a lot because we had a 40, 80, and 122 gears as our only choices 2 years ago. Now you can use whatever gears you want, but when you combine 40, 80, and 120, you tend to use a lot of either 3-to-1 or 2-to-1, or stack them up, cascade them to get 9-to-1, 4-to-1, 6-to-1.
Okay, so when you're doing electronics, one of the first things you always want to remember to do is tin your wires. This is so the copper doesn't fray. It's kind of a basic thing that you want to get in the habit of doing. Something very important, using power bus and redundant power supply. These kind of go hand in hand. On our robot, what we do, we, instead of daisy chaining all of our motor controllers, the power on our motor controllers, we do daisy chain information. We use a central power bus. This is a daisy chain. So you can see the battery power goes straight to that one, and then it goes to the next motor controller. So that's like a Christmas light. So on old Christmas tree lights, if one light went out, everything else down the chain was done. So the same thing can happen. If that first one dies, freezes, something happens, even if the other ones are all working fine, that could mean the rest of your robot's just done, not working. So this way we can always ensure that we have power going to all parts of our robot. Go back to work. Okay, then charge batteries. This is also part of always having enough power. With the charge, you always want to make sure you have a fresh battery before a match. So in between matches, you'll always be charging batteries. When we go out to a field, we'll have the charged battery waiting, and we won't put it in until right before we go on the field. This way we have maximum voltage to work with, so our robot has the most potential. And then finally, power supply and DC motor consumption. This is the idea of how you want to use your power. So if per channel on a motor controller, you can have 3 motors before you can use two? Oh, okay. 2 motor. Yeah, you can fully power 2 motors. So if you put more on there, that means they're not going to be able to burn out, but you're not going to be giving them full power. So it depends. If you want to give them full power, you put 2 on each channel of the motor controller. That way they can be working at their maximum